Hi everyone and welcome back to my channel in Economist. So in today's video, we are going to learn about how to estimate the model parameters of a multiple linear regression model using the matrix notation. So if you are someone who is following my playlist from quite a time, you will know that we have already done the parameter estimation in case of classical linear regression model and multiple linear regression model. We have made a separate playlist on that. I will give the link in the description, also in the I tab button. If you haven't seen that video, please check that out before going into this video. Now, in this video, we will learn the same concept, but using the matrix notation. We will know that if the model in the multiple linear regression model is given in the matrix notation, then how will we do this parameter estimation? And I have made one previous video for that, where we have talked about how to convert our usual model in the matrix form, right? This is the first video of this particular playlist. If you haven't watched that video also, then also I will recommend you to check that out and then come back to this video, right? So let me give you a quick recap of what we have done in the previous video. So we have taken a model like this. The model looks as usual. Yi is beta 1 plus beta 2 x2I plus beta 3 x3I all the way up to beta k xki plus ui. Right? This was the original model that we have used. And if you remember in the previous video, we have converted this particular model into a matrix form, which has given us this reduced form like this. Y curl is basically X beta curl plus U curl, right? So we have got this reduced form where this curl represents the vector. Y is the vector of from I from 1 to n. So I should write this thing. So I is from 1 to n, right? So y1 was what? So this vector y was written as this, basically y1, y2, all the way up to yn. And we have said that the dimension is n cross 1, right? This was the outcome vector. If you remember, we have told that this is the outcome vector. And then we had the design matrix. Design matrix looks something like this. The first column is 1 all the way through. Then you have x21, then you have x31 all the way up to xk1. Then you had x22, x32 all the way to xk2. And here we have all the way up to x2n, x3n, and all the way up to xkn. So we have said that this is the design matrix, the matrix of all the coefficients of the explanatory variable basically. So basically this X matrix here is known as the design matrix, which has a dimension of n cross k. And then it was multiplied by the parameter vector. Here you have k number of parameters, beta 1, beta 2, all the way up to beta k. K number of parameters, this is the parameter vector, dimension is k cross 1. And plus we had the error term or the error vector, which is u1, u2, all the way up to un, and this was n cross 1 vector, right? So this was the model setup that we have done in the previous video, and it is very important to note the dimension. So y is basically n cross 1, x is basically n cross k, beta is k cross 1, and u was n cross 1, right? So this is where we stopped in the previous video. Now what is our task? Our task for this video is to estimate the values of this parameter vector. This is the parameter vector. So beta, basically beta curl represents the parameter vector where you have k number of components. Since it is a k cross 1 vector, it is k number of components, b1, beta 1, beta 2, all the way to beta k. So you have to find out what will be the estimated values of all the k components. That is beta 1 cap, beta 2 cap, all the way to beta k cap, right? So this is what we will do, and we will estimate the model parameters. For that, let's see how will we do that. So we'll use the least squares criteria only. Let me write it down. Least squares criterion. What will be the least squares criteria for that? The criteria is we will choose the beta so that the quadratic form the quadratic form S, where S is simply y curl minus x beta curl transpose into y curl minus x beta curl. This particular thing is as small as possible, as small as possible. That is, S is minimum. So this is the least squares criteria. Understand this thing. What we have done is that we have taken this S as a quadratic form. So if you can compare this with the original forms that we have discussed, this is the residual sum of square basically. This is simply the residual sum of square. So in matrix notation, whenever you want to square sum, when you want this kind of a form, basically this is u I cap square. This is the residual sum of square originally that we have discussed previously. So ui cap square is the summation of the squared terms. So here also, if you put this transpose, here, it represents only this particular form, right? So basically, for example, if I do this x1, x2 up to xn, suppose this is one vector, and then you take the transpose of the same vector, x1, x2 up to xn. Right? If you do this thing, what will happen? You can multiply this. This is what is the dimension of this? This is n cross 1, and this is 1 cross. So here what you have, here how many rows you have? You have only one row. And here what you have? 10 columns, and here you have this. So what will be the form? It will be multiplication. So firstly it will be x1 square plus it will be x2 square all the way plus up to xn square. So it will be a 1 cross 1. This will be a scalar quantity, right? This will be a scalar quantity. That is the exact thing that we are doing here. We are taking the transpose of the first matrix and then we are multiplying the second matrix as it is. So it will give you a scalar quantity that you want to minimize. So you want to basically find out what will be the value of beta. What will be the value of beta that basically minimizes this particular expression, right? So I hope this is clear. Now, when we will solve questions, we will take particular values of this form and then we will try to see what will happen, right? So as of now, please understand that this is nothing but the residual sum of square which is written in this quadratic form. So we want to choose that particular beta which will minimize this quadratic form so that S will be minimized, right? So if you have to minimize this S, now what we will do? Simply first expand this thing. Now understand what is A dot beta transpose. What will be this? This is simply beta transpose into A transpose. This is the product rule of using transpose, right? So if you multiply this S expression, what will be the first expression here? It will be simply, firstly, you will have y curl prime. So you are taking the transpose inside basically. So y curl prime minus x beta curl transpose. X beta curl transpose will be beta curl transpose into x transpose for this particular rule, right? AB transpose is B transpose A transpose. So X beta curl transpose is beta curl transpose into X transpose. So this will be the first term and the second term will be as it is. Write it as it is. Now the second thing that we will do is to multiply. Just simply multiply this form, what you will get. First term is this. The second term will be beta curl X prime Y curl. Then you have minus Y curl So we are basically multiplying this with this, then this with this, then y curl x beta, and then you have plus beta curl x prime x into beta. Right? Have I done this right? Please check. Y curl prime y curl. These two terms we have taken first, and then we have taken these two terms. Beta curl transpose x transpose, then you have y curl. Then this term and this particular term, so y curl, then x beta curl, and then this term and this term. So beta curl, x transpose, x into beta curl, right? So this will be the multiplication. Now, From the first day, I'm telling you that the dimensions play a very crucial role. Now you will understand this, why dimensions play a crucial role. So basically, you have to find out what will be this particular thing, right? Now, let us first see what are the dimensions of each of these particular terms. So the first term is basically y curl prime y curl. So what will be the dimension? If you remember what is the dimension of y, this is simply n cross 1. So n cross 1. So what is the dimension of the transpose of that? This is 1 cross n. So what will be the dimension of this product? It will be simply 1 cross 1. So it will be a scalar quantity, right? It will be a scalar quantity. Now see for the second term, beta curl transpose, then you have x prime y. So what is the dimension of beta curl? Beta curl is k cross 1. So it will be simply 1 cross k. What is x transpose? N cross k, so it is k cross n. And what is y? This is n cross 1. So can you pause the video and think what will be the dimension of this entire term? See, k cross n will give you 1 cross n. And then you have n cross 1 cross. So again, what will be the dimension? This n matches, so it will be simply 1 cross. So the first term is also a scalar quantity. The second term is also a scalar quantity. Now let's look at the third term. Y curl x beta. So what is the dimension of n? Y is simply n cross 1, x is n cross k, and what is beta? This is k cross 1. So what will be this? So this is n cross 1, and then you have n cross 1. There should be some mistake. So this is y, this should be so this should be a transpose here. Y curl transpose, then you have x beta here. So this is transpose. So it is basically 1 cross n. So I'm just finding out what will be the dimensions of each of the terms. You can do this for yourself. This is 1 cross n cross 1. So it will be again 1 cross 1. And finally, the fourth term is beta curl transpose. Then you have x transpose x. And then you have beta curl. So what is the dimension? Beta curl transpose. Beta curl is k cross 1. So it will be 1 cross k. Then you have n cross k. So k cross n cross k. And then you have k cross 1. So what will be the dimension here? So first two terms, it will be 1 cross n. Then your next term is n cross k and k cross 1. So again, first two terms, 1 cross k, and the next two terms will be k cross 1. So it will be simply 1 cross 1. So what you see here is that, what is the main motive of doing all these things is that you see that all the four terms that we have got in the product form are scalar terms, right? All the four terms here, all the four terms. So if you take the product of these two things, you will get four individual components. This is the first component, second component, third component, and fourth component. And what we have done so far is that we have found out that all these four terms are scalar in nature. All the four terms, since it is 1 cross 1 means only one row and one column means only one component. It's a number. Basically, they will all come out to be a number. So when they are scalar terms, can you add and subtract them? Answer is yes. If this is a scalar term, suppose the first term is 2, the next term is 3, the last third term is this, and the fourth term is this. So if this is the case, they are all four quantities are scalar in nature. So you can basically add and subtract them, right? So this is what we found out. So if we have this information, then in order to add them or subtract them, what we need similar components. So see which of the following terms have the similar components. Can you find that out? Which of the terms have similar components? If you see, the second term and the third term will have similar components. See, in both the terms, you have a term of beta curl, you have a term of x, and you have a term of y, right? Beta, x, and y, they are present. Yes, there are some components, some transpose of them, but that doesn't matter because see, the components remains the same. Even if you take the transpose, the components remains the same. That is why we can basically add these two particular things. We can add this particular thing and we can write the value of s to be like this. See, How will I write this? S will be simply, okay, let me write what we had. Y curl Y, this was the first term. Then we have beta curl transpose X, Y. This is the second term. Then you have Y curl transpose X into beta. This is the third term. And the fourth term is beta curl transpose X prime X into beta curl. So this is the fourth term. So what I am saying is that we are able to add these two things so that we can write what we can write. This will be 2 into beta curl transpose into X transpose into Y. And then the next term will be as it is. Right? So this is the only thing that you need to understand, because the rest of the thing is very simple, right? If you understand this much, your main thing is done. So you can basically pause the video, think for yourself what I have done. And if you have any questions anywhere, you can let me know in the comment section, right? So I have just added these two things. Since they both have the same components and they are scalar in nature, they are basically equal. We can treat them as equal terms, right? We can treat them, they are both scalars and they are equal to each other, hence we can add them. Now the last step would be, suppose we assume that beta cap is the vector, of estimated coefficients. So what you can simply do, you can simply take the partial derivative of this s with respect to beta and put beta equals to beta cap, right? So wherever you have beta curl, you can put this beta curl cap, you can put this curl here because they are all vectors. So beta curl cap is the vector of estimated coefficient. So you will take the partial derivative of this s with respect to beta, and then you will put beta equals to beta curl and set it equals to 0. If you do that, see, in the first term, there is no beta. So you'll eliminate that. In the second term, there is a term of beta. So it will be simply 2 into x transpose into y curl, right? If you take, so transpose again doesn't matter. If you take the differentiation, the transpose doesn't matter. Only this much will be there. Plus, see here you have beta curl 2 times, right? Beta curl 2 times, so that will be squared basically. Beta curl transpose into beta curl, that will be treated as beta curl squared basically. So it will be 2 times beta curl cap, and then you have x prime into x. Can you see this thing? Please try to observe this thing well, and then we will set it equals to 0. So here you have two components of beta. We will treat it as square. So that is why it is 2. So what is this? D beta of beta square will be 2 beta basically. So that is what we are using here. 2 into beta curl. Now you will compute the beta curl at beta curl cap basically. That is why we have put this cap here. We are computing it at this beta cap. So that is why this particular term comes. Now, if this is the scenario, we can clearly find out what will be the beta cap then. So 2 into beta curl cap x. This will come out to be 2 into x and to y. So this 2 and 2 cancels out. So what is the estimated value of beta? What will be the estimated value of the parameter vector beta? This will be simply x transpose x inverse into x transpose y. And all the questions that you will solve after this will be dependent on this particular formula. This is the formula of the estimation. This is the estimated parameter in case of multiple linear regression model using matrix notation. While this X represents the design matrix, this we have discussed in the previous class also. X is the design matrix and Y is the outcome vector. So if you know the components of the design matrix, if you know the components of the outcome vector, you can clearly find out what will be all the parameter values. This is k number of parameters. Beta 1 cap, beta 2 cap, beta 3 cap, all the way to beta k cap can be found out using this particular formula, right? And now you can ask me that how do you ensure that this inverse will exist? Can you tell me how can we ensure this thing? This also we have given the explanation in the previous class. If you remember, in the previous class, I have said that one of the assumptions of multiple linear regression model is that X should be of the full rank. Remember this thing? We have described this in the previous class. If you haven't watched again, I would recommend you to see that. So we have said the rank of the design matrix should always be a full rank. That is, all the rows and the columns of the design matrix should be linearly independent of each other. If this is the case, then definitely the determinant of x prime x exists, right? This will be not equals to 0, and hence the inverse also exists. This inverse always exists, right? So that is why this full rank assumption is very, very important. I have told you previously that this will come handy when we will study the parameter estimation, and that is the usefulness of this assumption. That if you assume the full rank matrix, if you remember in the matrix, in case of Kramer's rule also we said this, that if the matrix is of full rank, then only the determinant is basically it is a non-singular matrix. In that case only, if the matrix is non-singular, then only we can say the inverse exists, right? That is why we can definitely say that if x is a full rank, then x prime x inverse this matrix definitely exists, and hence this parameter estimation is valid in nature, right? I hope this much is absolutely clear. Now, the final thing that we will do, which is also very important, we will find out the distribution of this beta cap, right? This estimated parameter, the estimated value of the parameters will follow certain distribution. So, in order to find out distribution, we will find out the mean and the variance, right? So, we will follow the same rules that we have followed previously, and we will see what is the expectation of this beta curve cap and what will be the variance of this beta curl cap. This will give us the idea of what will be the kind of distribution. What will be the kind of distributional properties of this beta cap, right? So for that, let us start. First property will be property 1 is that beta curl cap is unbiased. Beta curl cap is unbiased estimator of beta. So this is the first thing that we are going to prove. Now, how do you prove that? So start with the thing that we derived just now, x prime x inverse x prime y. This is what we have. This is the estimated parameter estimation that we got. Now, what you will do, instead of this y, put the value that you have from the original model. This was the original model. Remember this y curl is what? If I go back, see, y curl is this. Y curl is x beta curl plus u curl. So that is what you will replace here. Instead of y curl, replace this and then take the multiplication. So x prime x beta curl, this will be the first term, and then you have x prime x inverse x prime, and then you have u curl. X prime, and then you have u curl, right? This is what you have. Now, if you see what the here in the first term, see, this is x prime x inverse, and then you have product of x prime x. So can you tell me what will be this? If you have A inverse A, what will be this? This will be simply the identity matrix, right? A inverse into A, that will be simply identity matrix. Now, if you multiply identity matrix with any other matrix, what will be the value? Only that matrix will come out, right? Identity matrix, if you multiply it with any other matrix, then that matrix that you are multiplying with, that will come out. So if this is the case, then what will be the value here? Here the value will be only beta curve, right? Here the value will be only beta curl. So this product of these two things will be identity into beta curl will simply give us beta curl. And now this term is as it is. Right? Now, if you have this particular term, now you can take expectation on both sides, right? We will take expectation on this particular term, and when we will be able to find out what is the expected value of beta curl. So expected value of beta curl cap will be simply expected value of the entire thing that we found out, x prime x inverse x prime into u curl. That is what we got earlier. See? Yeah. Now expectation will be on individual terms. Expectation now, see that here this x is non-stochastic. In the second term, x is non-stochastic. It's a scalar quantity. So expectation will not be on that. Expectation falls only on the random variable. So here you will have only expectation of u curl. Now this beta curl is the population parameter, which is a constant. So basically a scalar quantity. So expectation of beta curl will be simply beta curl plus this expectation, this remains the same, x curl. Now can you tell me what will be this? This is also one of the assumptions of CLRM that we discussed on the previous class. This will be simply zero curl. Now, if you multiply anything with zero curl, the entire thing becomes zero. So it will be basically beta curl plus zero curl, which will be simply equals to beta curl. So that is how you prove the unbiasedness, that expectation of beta curl cap will be exactly equals to the population parameter, which is beta. Right? This is how you prove the first property. I hope this much is clear. So firstly, we have understood how to find out the parameter estimation of beta. The formula is this. This is what we got. Now from that parameter estimation, you can find out what will be the expectation of beta and what will be the variance of beta. So what is the expectation? Expectation of beta curl will be simply equals to the actual population parameter, which is beta curl. That is why it will be an unbiased estimator. This will be an unbiased estimator of the two population parameters. And the final thing that we will do in this video will be to find out the variance. For variance, we will find out something called the covariance matrix. We will do something called the covariance matrix. What is covariance matrix? The covariance matrix that expresses the sampling variability of the random vector beta cap curl is defined as, what will be the term? The term will look like this: expectation of beta curl cap minus expectation of beta curl cap, and then, so let me put it in one bracket, and then you have beta curl cap minus expectation of beta curl cap, and then finally you have a transpose. See, again, the same concept, transpose acts as a, squared agent, right? If in the normal terms, you can write summation and then put a square. But if you are working with a matrix notation, your transpose will act as a square. So this is basically the same as writing this. What is the variance of X? If you want to see what is the variance of X, usual formula, variance of any random variable, this is simply expectation of X minus expectation of X and a whole square of that, right? This is the formula. And see, this expression that we have written in matrix form exactly resembles this. So instead of square, to make it square, so see, it is expectation of X minus expectation of X into X minus expectation of X 2 times. And that is the same thing. See, this is the first term and this is the second term. Here you have a transpose. This transpose will act as a squaring agent, right? This will basically a squaring agent. Now this X is here, it is beta curl cap. X is basically beta curl cap here, and expectation of beta curl cap everywhere it is the same. So you can basically compare these two things if you find this expression a little difficult, but it's not that difficult. I hope you got the process that why we are doing this. So this will be the term. Now see how will we handle this thing? Expectation of. See, what will be beta curl cap? What will be the expression of this? What will be the expression for this? Now remember that we only know, as of now, we only know the distribution of U curl, right? We only know the distribution of the error term or the error vector, which is U curl. We have said that the mean is zero. Mean is a zero vector, and the variance we have found out is sigma square into IM from the variance covariance matrix in the previous class we have discussed, right? So we have to convert. If you want to find out what will be the distribution of beta curl cap, then you have to rely on the distribution of U curl cap only, right? So because that is the only distribution you know. So what we do, we will convert each of the terms in terms of the U curl, right? We will convert these terms in terms of U curl. So for example, so beta curl, if you see from this, okay, so this is, let me go here, yeah. So from this expression, see, beta curl cap is this, and we just found out expectation of beta curl cap is beta cap curl, right? So if you take the subtraction, what will you get? You will get this particular term. See, this minus this term minus this term. If you do, you will get this term, and then you can replace this entire term. This term is as a function of u. This term is a function of u. That is why you can replace this particular thing here. I hope this is clear. If you have any doubts, again, I am telling you, you can let me know if you have any doubt in any of the steps that I am doing. I'll clarify that. So this will be the first term. And then you will take the transpose of this exact similar term. Right? This is what you will get, x prime, x inverse. Then, okay, so you have x transpose here. So it will be x transpose into u curl, right? And then finally you have this transpose. Now again, you will do what you will do. You will take the transpose in the second expression and simplify this. So the first expression remains the same. Now come to the second expression. This is the first expression. Come to the second expression. Start from the last term. So the transpose will be firstly on this, then on this, and then on this. So what is u curl transpose? So u curl transpose as it is. Then what you have, x transpose will simply be x, right? X transpose and the transpose of that. If you take the transpose of x transpose, you will be returned the original matrix x. So that is why it is only x. Now the inverse and transpose doesn't matter, so it will be simply this inverse, right? So this will happen. Now see, expectation is there. Expectation will be only on the random variable. That is only random variable is u curl. So let us do that. So expectation. So what we will do, x prime, x inverse. Then you have x prime. Then you have expectation on u curl transpose. And then you have x. And then you have x prime x and the inverse of that. See, this is what we have done. So we have only taken expectation on these terms. Rest of the terms I have written as it is. So it will be x prime x inverse, x prime. Now can you tell me what will be this? This we have seen in the previous class. This will be simply sigma square into in. This we have done in the previous class. If you don't know, I'll upload. I have already uploaded. I will give the link in the description. See that. Okay, now this much is done. Now you can put this sigma square out of this entire thing. Now see what are the terms left. Sigma square in, this will come out. So x into x inverse. Then here you have x into x. And then again you have x prime x inverse. So sigma square. Now what will be this term? This term will be simply identity matrix. So don't need to write that. It will be simply x to this. So what we see is that expectation of beta curl, expectation of beta curl into beta curl minus expectation of beta curl and a transpose of that, this will simply come out to be this. And this is nothing but the variance matrix, the covariance matrix basically. This is known as the covariance matrix. This is basically the covariance matrix. So what we can basically say from here is that beta curl, what will be the distribution of beta curl? Beta curl will follow a distribution which has a mean of exactly equals to the population parameter beta curl, and the variance will be simply this. Right? So this will be the distribution, and the variance we found out from this particular expression. Variance we found out from this particular expression. Now, why this is called the covariance matrix? If you want to expand this matrix, right? If you expand this, what you will get is something like this. Observe. If you basically expand this, you will get something like this. Let me write it down. First term will be beta 1 cap, beta 1 whole square. The second term will be beta 1 cap minus beta 1, beta 2 cap minus beta 2. And the final term will be beta 1 cap minus beta 1. You have total k number of parameters. So beta k cap minus beta k. And everything will have a curl. Everything will have a curl. So you may not write it because we are talking about the individual parameters here. So you may not write this curl here. So this is the first term. The second term will start like this: beta 2 cap minus beta 2. Then you have beta 1 cap minus beta 1 cap. All the way up to the final term will be beta k cap minus beta k, beta 1 cap minus beta 1. The second term will be simply beta 2 cap minus beta 2 whole square. Here you will have beta k cap minus beta k and beta 2 cap minus beta 2 and beta 2 cap minus beta 2, beta k cap minus beta k. The matrix looks something like this. And final term will be beta k cap minus beta k whole square. Right? So this will be the entire covariance matrix. And now if you individually take the expectation, of each of these particular terms, all the terms, you will have something like this. What can you tell me? Expectation of beta 1 cap minus beta 1 whole square is what? Pause the video and think this will be simply beta 1 cap. Similarly, for all the diagonal elements, the first diagonal element is this, the second diagonal element is this, so it will be simply variance of beta 2 cap. So all the way through, the last diagonal element is this. This will give you the variance of beta k cap. So in this matrix, the diagonal elements will give you the variance and all the rest of the terms will give you the covariance. This is one covariance, this is one covariance, all the terms will give you the covariance. So this is basically the covariance of beta 1 cap and beta 2 cap. Finally, this will be the covariance of beta 1 cap and beta k cap, right? And all the way through, this will be covariance of beta 2 cap, beta 1 cap, covariance of beta k cap, beta 1 cap. And here you can fill all the covariances. Basically, what we are trying to say is that the diagonal elements will give you all the variances and the off diagonal elements will give you all the covariances basically. That is why it is known as the covariance matrix or the var covar matrix. And this is what we are trying to find out. So if beta curl is like this, if beta curl is following this particular distribution, what is the distribution of y? What will be the distribution of y? Y will have a mean of x beta curl and the variance will be simply equals to the variance that we got for the u curl. And u curl will follow a distribution which has a mean of 0 and the variance will be simply sigma square into I. Right? So this is all from my side today. I hope you find this lecture helpful. So let me do a quick recap of what we have done. Let me take you through what we have done. So firstly, we have started with the parameter estimation where we have done a quick recap of what we have done in the previous video. We have started with this kind of a model and we have seen what will be the matrix notation looks like for this particular model. Now, we have gone into the least square criteria where we took the residual sum of square in the matrix form. This is the residual sum of square in the matrix form. And we have found out step by step, we have learned the process how to calculate, how to find out the estimated value of this beta curve in case of matrix notation. And we found that this will be the final form of that. Now, once we have this estimated value, we can find out the properties of this estimated value. We have learned how to find out the mean of that estimation, right? The expected value of this estimation, and we have seen it is exactly equals to the population parameter, which is, following the Gauss-Markov assumptions. In the next video, we'll talk about that. What is Gauss-Markov assumption and how will you prove the Gauss-Markov assumption in the matrix notation? And this is the process. And here, in this way, you can prove that expectation of beta curl will be simply equals to beta curl. And then we have gone into the variance portion. And variance in case of matrix, you cannot find out the individual variance of all. You have to find out the var covar matrix. So in order to do that, we will start with the formula of variance. This is the expression. This is, you can compare it with this expression in order to, compare in order for your convenience. And then we have seen step by step how you derive the thing. And this will be the final. Final matrix will look something like this. Sigma square x prime x inverse. This will give you the variance of this error term. Sorry, variance of this estimated parameter values, right? Estimated parameter value will follow the distribution where mean is simply beta curl, that is why it is unbiased, and the variance will be simply given by sigma square x prime x inverse. And this x inverse, x prime x inverse exists because x is a full rank matrix. Design matrix is always full rank. This is by the assumption of CLRM and MLRM also. in case of matrix notation. And finally, we have seen how this bare covariance matrix looks like. This is the entire covariance matrix where see the diagonal elements. All the diagonal elements here will give you the variances of the parameters, and all the off diagonal elements will give you the covariances of the parameters, right? So this is the entire thing that I wanted to share with you. I hope that you like this video. If you do, hit the like button and do subscribe to this channel in Economics, because that gives me immense motivation to make such useful videos for you. And for more videos, if you want to see more of these videos, do comment below that yes, I'm finding this helpful. I want to see more of this. And I'll make a complete playlist on this model, right? So thank you so much for your time. And let's meet you in the next video where we will go into the Gauss-Markov theorem, and also we'll solve numerical questions on this parameter. Thank you so much.